Today's lesson is 9.4, Preparing Solutions. Preparing solutions. So here in when we're preparing solutions, these are the steps that typically at the high school level we typically we prepare the solutions for our students for labs. But come post secondary, a lot of times you're gonna have better facilities in a post secondary. That's where your money goes to, right? At the high school level, we wouldn't dare allowing students to dilute strong acids because typically a lot of chemicals come highly concentrated. Okay, so in 9.4, we're going to look at how to dilute these solutions. Okay, so typically when we buy chemicals for the lab in high school, okay, we typically buy what's referred to as stock solutions, and these stock solutions are super concentrated chemicals. Acids are typically bought that way. So acids are bought at very highly, at very high concentrations. We might buy hydrochloric acid at 12 moles per liter. Okay, so we might buy hydrochloric acid at 12 moles per liter. This is a very concentrated acid. If you were to pour this out, you would have to be working in a fume hood. Okay, fume hood, because the fumes from such a highly concentrated acid is very corrosive, so it could actually start to eat away at your insides as you're inhaling it. So that's why we would never dare, and especially if you remember our class, that fume hood is very small, so really only one person really at a time can actually be working in that fume hood. And at post-secondary, typically you'll have rows of fume hoods for students to be working at. I remember at my university there were many in the lab, and they were big enough to allow for our lab partners to work. But again, we buy these at very concentrated, and we extract very little of it, and we dilute it with water to lower this concentration. Okay, so what we are really doing is, imagine we've got 12 moles per liter. So let's say we have 12 liters. We have 1 liter and we've got 12 moles of an acid. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So let's say we've got 12 moles. This represents 12 moles of that acid. When we dilute it, okay, when we extract, it doesn't matter how little we pull out, it still has 12 moles, okay, per liter. But the only difference is if we dilute it, right? If we dilute it in water, those 12 moles are now further spread out. So we've got, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so notice here, when we're diluting, we're kind of spreading out that concentration with water. So we're softening up the strength, okay, the concentration of an acid, of a base, of some kind of chemical. Okay, so acids are commonly purchased as stock solutions. Same thing with bases. So what we're doing is we are diluting them, and we're diluting them with water. But one thing to make note of, and I don't know if it's on this next slide. Let's see, is it? No. One thing to make note of, and the rule of thumb is this, and let's do it in a different color. We are always add acid. Acid to water and never water to acid. Okay, it's always acid. We mix the acid and we prepare how much water we need ahead of time, so we know. So we're using these calculations. We know how much water we need to extract to properly reduce their concentration to the desired concentration. Okay, why do we not add water to acid? And we don't add water to acid because in that order, it's a very exothermic reaction, which means it's going to heat up, and it could heat up, the beaker can heat up to the point where an explosion of like that beaker could explode because of all the energy. Okay, and you don't want acid splashing at you. Okay, so that's one of the safety features when diluting an acid. Always remember you're adding acid to water, never water to acid. Okay, so when we're writing or when we're diluting a stock solution, okay, we are using the following equation. C1 V1 equals C2 V2. Remember the equation that we just saw here. C is equal to N over V. Notice the one unit missing. The one unit missing is our N value, and because the N value is really the same between both of them. Okay, the only difference is, right, remember here, this is 12 moles, let's say, for every liter. This case here, maybe this is 12 moles for every, I don't know, maybe we have 24 liters. So if we divide these two numbers out, our concentration of acid is going to be so much less, but the number of moles is no different. Okay, so notice how the number of moles don't change. The only thing that changes is the volume of our solution, which will result in a change in the concentration. Okay, so this is the equation that we're going to be using. So what we have here is the two states. So this first here, this is our initial state, which is going to be typically your stock solution. This is going to be where your highest C value will be found. And this is your final diluted product. Okay, so this is the dilution. Okay, so this is going to be the lower concentration value. Okay, in this case, the units don't really matter for volume. However, just make sure that your volume units are both going to be the same. So if I give you a problem like this, and I give them to you the volume in liters, you can keep them at liters. Okay, you can keep them at liters, provided that the liters are what's going to cross out. Okay, or milliliters, sorry, as long as they cross out. But you'll see when in the sample problems, I think I might have a sample problem where we discuss that. Okay, now when we get to the stoichiometry, and we're going to see stoichiometry for solutions in the tail end of chapter 10. Okay, so we start chapter 10 on Monday. So chapter 10 on Monday, you are never using this equation in your formula. This equation is only for diluting a concentration. It has nothing to do with a chemical reaction. Okay, so make note of that, because sometimes students will use this equation. Believe it or not, sometimes it works, sometimes it doesn't work. And that's the reason why we don't use this formula. Because if we use this formula, we're not acknowledging the mole ratios. Okay, notice there's no N value here. Okay, but when we do stoichiometry, we are always trying to find that N value, and we're using it to find the mole ratios. Okay, and we need to know those mole ratios, because those mole ratios can change the value, and that's the reason why sometimes this formula will work, sometimes it won't. So that's why pretty much if I ever see this in a stoichiometry problem, I don't mark the stoichiometry problem. I mark it wrong, because you're clearly not using the formula correctly. Okay, so make note of that. Hence the reason why I said note. Okay, so here are some sample problems. We're going to look at, actually, we're going to look at sample problem number 2. Okay, sample problem number 3 and sample problem number 1, they're the same. And really, 1 and 3 are no different to 2, but the difference with 2 is in 2, I actually ask you to explain in words how you would prepare this solution. So anyhow, let's ignore that part. We're given a volume. Look at that concentration. That's high of an acid. And we want to prepare 500 milliliters for a class, but we want to lower this concentration from this. Okay, so this is our C1 to a C2. Okay, so again, great thing to start off is, list your information. Okay, so in this case here, our units, again, we decided here, I changed my milliliters to liters just to kind of as a force of habit, since we're most of the times, 95% of the times, we're going to need to do that. Anyhow, we substitute into our equation, okay, and we get this volume, okay, which is in milliliters. Okay, so I converted liters back to milliliters because how am I going to prepare this solution? So if I was to tell someone, okay, I need you to calculate for me 0.0781, that's going to be impossible to measure with any of the beakers, any of the graduated cylinders you'll find in a science lab. Okay, so that's the reason why I converted it back to milliliters, right? Because when I'm demonstrating here. Now, this is how much of this highly concentrated acid I am going to pull. Look at how little it is, 78.1 milliliters of it. But the solution that I want to prepare for my class needs to be a total. Okay, so understand that this is the entire solution. Okay, so this here is the entire solution. So my solute is the nitric acid. Okay, so the solute is the nitric acid. My entire solution has to be 500 milliliters. Okay, so of this 500 milliliters, 78.1 milliliters needs to be part of that, which means I am going to subtract 500 with 78.1 to give me 42.19 0.9 milliliters of water. So that is how much water I'm going to have in a beaker ready, because I need to have my water ready. Because remember, as we said, we always add acid to water, never the other way around, because water is exothermic and can cause the beaker to shatter. Okay, so we want to have the amount of water ready, because when I add this 421.9 milliliters of water to 78.1 milliliters of this highly concentrated acid, I will end up diluting that acid to this lower concentration, and I will have 500 milliliters. Notice I am not adding 500 milliliters of water to this, because then my whole volume that I will have will be 578.1 milliliters of an entire solution. Okay, this is the solution. That is the solution of the solute and solvent together. This here, all of a sudden now, that will actually lower the concentration even further, because I am not putting the proper amount of water to get this actual concentration. Okay, so can't stress enough. Practice the questions found at the end of the lesson. Okay. I hope you liked this video. If you did, do not be shy to hit that thumbs up button. And while you're clicking the thumbs up, click on that subscribe to stay tuned to my new videos. Thanks for watching.